Okay, so balanced and unbalanced forces is kind of part two here. So we talked a little bit about what forces are. Forces are vectors, what types of forces there are, contact ones versus long distance or non-contact forces. I showed you a little bit how to label forces, make free body diagrams. Now we're going to talk about the key part of motion, and how motion and forces are tied together, and that's balanced and unbalanced forces. So, like I told you guys in the last video, forces cause motion, and more specifically, right, forces cause objects to accelerate. Okay, and that could be speeding up. Hello, pen. There we go. Speeding up or slowing down. Okay. So what we're going to look at here is kind of how that happens. Okay. So let's start with a really simple example. And that really simple example is going to be a box. And that box is going to be sitting on the ground. Okay. Now, you may have heard me reciting Newton's first law of motion to you in the last video. Newton's first law. Newton's first law. We'll just write Newton's one. Okay. Well, we can write Newton's first because we're not heathens. Newton's first law. Okay, so Newton's first law is an object at rest, like this box, okay, it's at rest, will stay at rest unless acted upon by an outside force. It also says an object in motion will remain in motion unless acted upon by an outside force. So let's look a little bit at what that means, okay? Just from a perspective of how does motion work and why are forces involved, and then we'll do some quick examples and we'll be done. This will be a short one. Okay, so this object is at rest. Nothing is going to cause this object to move at all until something comes along and does, right? So let's put a person right here. And that person's going to have exceptionally long arms, again, because I'm just the world's most amazing artist. Also, they have, really bad scoliosis and very weird hands, hook hands, if you will. Okay, so there we go. They're gonna push this. They're gonna push this thing, okay, to the right. All right. They're applying a force on the box. Now, eventually, they'll be able to push the box. So Newton's first law is also called Newton's law of inertia, right? So there is an amount of force that is required to move this box, and it's based on the weight of the box. Okay. So the weight of the box is, and the friction that between the box and the ground, right, will cause the box to essentially resist motion until there's a certain amount of force. But once you put some force on the box, it's going to start accelerating, right? Same thing is true. Let's use blue here. So let's say this is ice, okay? Ice lowers how much friction there is between surfaces, right? So if the box is now on ice, like this, and the box is already in motion, okay, that indicates that it's in motion. So it's going to the right. Hello, there we go. The box is moving to the right already, okay? So in a world where there's no such thing as friction, if there was no friction at all, friction is a force, right? So there's no force acting on this box right now, aside from gravity pulling it down and normal force pushing up, right? So those two forces are there. But in this case, the object is moving to the right. Let's say that there's no friction because it's super icy and it's on a planet where friction doesn't exist if there's ice. I don't know. Not technically Earth, because there is technically friction, but just go with it, okay? This object would continue moving always and forever until something came along to stop it, like maybe this giant wall right here. If the box were to hit that wall, then the box would slow down very quickly to a stop, or it would at least bounce, right, and change directions, which is also accelerating. So acceleration is speeding up, slowing down, or changing directions, which you'll learn or should have known by now from graphing motion. So if you didn't, now you do. Okay, so those are some quick examples of how Newton's first law works. Okay, but let's look at some problems, right? So let's go back to our box. Box touching the ground. Hooray. Okay, let's diagram the forces acting on this thing, shall we? So we know that there is gravity. Okay. Woof. Here we go. FD. We also know there's a balanced force, normal force, and I'm breaking my own like convention here and using an actual box when I probably should have used a dot, like I said I like to do, but we're going to use the box because it's easier. Okay, so technically then you wouldn't need these on the side. You would do them from the top and the bottom of the box, and that's fine. Okay, so those are balanced right now, right? This box is sitting still. Currently, the forces are balanced. Okay, how do we know? Because the acceleration of the object is not changing at all, right? These forces are balanced. The same thing is true on the box that's on the ice. It has the exact same force diagram, actually. It would have normal force up and gravity down equal to each other. They're equal, they're canceling out, right? So for those of you who are in geometry, you're probably used to, or if you do algebra and you've talked about line segments, you're probably used to seeing things like this, indicating that these lines are the same in magnitude, right? That's kind of what those symbols mean. So these things are the same size. So they cancel each other out, basically. Okay, those forces are balanced. Now, let's say an object has unbalanced forces acting on it, right? So let's go back to that box. And well, there's our ground, and here's our box. Okay, so we're going to put gravity down again. We're going to put normal force up. Oops, I forgot to put arrowheads on the end. Sorry. Gravity down, normal force up. Those are balanced, right? But what if somebody's pushing on the box? Well, then you have an applied force. And check it out. This diagram is unbalanced, right? Okay. Wow. Unbalanced. Let's spell the word correctly, shall we? Unbalanced. Good. Since the forces are unbalanced, which way is the object going to move? Well, let's get a different color and experiment with that. The object's going to move quite quickly to the right. Why? Because there's an unbalanced force going to the right, right? So it's going to accelerate to the right. So that's something to think about. Okay. I meant to make that an arrow, but there you go. So unbalanced forces will do that, right? So let's look at some examples. Okay. So let's say that we've got an object. Let's call it a book, perhaps, and the book is resting on a tabletop. Okay. We have a book sitting on the ground. Great. All right. Sweet. So what forces are acting on the book, right? Let's make a free body diagram for the book right over here to the one side. Okay, so there's my dot. Free body diagram for the book, right? Force going down, force going up. Are they the same size? They are. We've got normal force, we've got gravity, right? Now, if someone starts pushing the book, right? So let's say that we're going to have a hand applying a force to the book. So let's bring a hand in here. We'll put some fingers on it and a thumb. Okay, it goes up to an arm and it's going to be pushing. Okay, so now we've got an applied force on the book, right? So we need another arrow pushing our book, okay, to the right. Force applied. There we go. That's what we've got. That's our force diagram. Is this object going to accelerate? Yes. Which way is it going to go? It's going to go to the right. Okay. Right now, let's talk about this from a numerical perspective. Let's say, so you can understand how it works numerically. All right. So let's say we have an object. And remember, forces are in newtons, right? So the unit of force is in newtons. So if we do a number, something like this, 10 newtons, that's 10 newtons of force, right? So let's say that's how much the book is being pushed by. So let's make our diagram again. Okay. We know we've got balanced forces up and down. And then we've got 10 newtons of force. So if this is 10 newtons, right? Let's say that maybe this is 15 newtons and this is 15 newtons, right? These forces are the same size, so they cancel out. So our book is moving to the right with a total force of 10 newtons. So what is the net force? So net force is the sum of the forces in a given direction. Okay, so we know that up and down forces are canceled out, so we don't say anything for that. So what's our net force in this case? It's 10 newtons to the right. Okay, it's 10 newtons to the right. So which way is our object going to go? To the right. How? With 10 newtons of force. So it should go, depending on its weight, right? If it was 1 kilogram, it would go 10 meters per second squared to the right. It would accelerate with 10 meters per second squared, which is pretty fast. Okay. So that's how that would work in terms of net force, right? So my job in terms of what the state says is to tell you only about single directions. So anytime we're going to have force in multiple directions, one side should be canceled out. Now, that becomes difficult when we put objects on a slope, right? So what if we put an object on a slope like this? Okay, can we make a slope, please? Yep. Okay, and now if we put an object on that slope, right? Let's say we put the book up there or some square, it doesn't really matter. So now things get weird, right? Because we've got gravity going this way, we've got normal force going at a 90-degree angle. We might have friction trying to keep us from going. Okay, so these forces are not anymore acting in like a straight up and down, left and right situation, and the forces might not be balanced in two directions. This problem is more complex. This one right here is more complex than what you need to know how to do. We might do one just for giggles, but we're not going to do it right now. Okay, so just keep in mind that that does exist, just like I showed you in the last video. There are more complex examples, but for this class, we're only going to be really studying single direction. If there's ever multiple directions, it's my job to tell you that these ones cancel out and that all that's left is this one. Okay, thanks for watching.